Okay, so now we're going to talk about something new that we haven't discussed before, and that's the confidence interval. Now, to do so, I need you to remember how we talked about the sampling distribution of the mean. If you remember, in our SDM, is actually is when you take all possible samples from the population of a certain sample size n, and every time you're going to calculate x bar, because basically that's what we're doing the sampling distribution of the mean. And if you meet certain conditions, the SDM will have a normal distribution, right? Okay. I mean, I know this is not perfectly normal, but please excuse me for that. And what do we know so far about this? Well, you know that right in the middle, you have the mean of the x bars, which, if you remember, is exactly equal to the original mean, and you have the standard error. And by now you remember that standard error is the standard deviation of the x bars, and it's equal to sigma over root square of n. And just to make sure that everybody remembers what I'm talking about, um, this x bar is coming from a population, and it's where I'm studying variable x, which has its mu and its sigma, and this mu and that sigma are exactly this mu right here and this sigma right there. Okay, now here's a question. If I want to find two values here and there, such that what's covered in between, so this shaded area, all of this, is actually 95% of all the x bars. Okay, so I want to find the upper and the lower value such that what I have inside is uh, exactly 95% of the x bars. Okay, meaning what is left is 5% of the x bars. Now the leftover 5%, since this is a symmetrical distribution, if you leave out 5%, well, half of the 5% is going to be here and half of the 5% is going to be here, right? So this area, if I'm going to shade it using, let's say, the orange, this area right here is going to have 2.5% of the x bars, and this area right there is gonna also have 2.5% of the x bars, because as we said, the distribution is symmetrical. Now my question is, how can I find this value? And I'm going to call it, this is x bar upper limit, and I'm gonna call this one x bar lower limit. Okay, so how do I find x bar upper limit, and how do I find x bar lower limit? Actually, we have done something similar to that when early on in the course, when we started talking about the Z, I've asked you to get the percentile. So I would ask you, can you find the 90th percentile? Can you find the 80th percentile? And the percentile is the value that cuts the data at a certain percentage. Okay, so here's my question. What is this percentile? If the lower value x bar has below it this area only, then the percentile of this value right there is 2.5%, right? Okay, so how about before I start finding x bar lower limit, I try to find z lower limit. My question, am I allowed to use the z? Well, look at the sampling distribution of the mean. Does it have a normal distribution? Yes, it does. Therefore, you can transform it into a z. Okay? All right, so let's try and find what z has an area below it, which is 2.5%. Yani, if I want to write the probability, this is the probability such that z below the value that I want to find, the area I get is 0.025. Okay, So this is going to be given to me by the table, the Z table. If I find the area, I find this unknown, and if I find this unknown, then I will be able to replace the Z. And remember, if you find Z, then you can find X bar. Okay? Question, is this what the table gives me? Yes, you have Z less than, and you have the area. So yes, you can use your Z table. So let's open the Z table. I'm looking for area 0.025. You start looking for area 0.025. Now here, that's too small. 0.025 still too small. 0.0202. I'm getting close, but it's still too small. 0.0256. I'm almost there. In fact, if I just look at this one right behind it, this is exactly the value I'm looking for. And that for Z equal to negative 1.96. Great. So I was able to find that Z lower limit is equal to negative 1.96. Now guess, if this Z lower limit is equal to negative 1.96, if I were to try to find Z upper limit, what do you think the value is going to be? Well, by now you know that Z is symmetrical, right? So, and these two values are symmetrical. So Z upper limit and Z lower limit are symmetrical, which means that the Z upper limit is going to be positive 1.96. Okay, Azim. So I reached a place. I know what are the Z values. Now I need to find X upper limit and X bar, I mean upper limit, and X bar lower limit. Well, remember the formula. The formula says that Z is equal to X bar minus mu over sigma divided by square root of n. صح? Okay. Now we found that Z lower limit is 1.96, so I can plug in here negative 1.96. Okay. And mu, I'm just going to leave it as mu, and sigma over root square, I'm just going to leave it sigma. So I'm going to rearrange all of this to get the X bar, and by doing rearrangement you will quickly find out that X bar, and this is lower limit, is equal to mu minus 1.96 sigma over root square of n. So this is the sigma lower limit. And if you try and find the upper limit using the same approach, you will quickly find that it's equal to mu plus 1.96 sigma over root square of n. Okay. Alright, so what does that all mean? Well, let me clean up a little bit and we will talk about what all of this means. So remember, I started up saying that I wanted to find X bar lower limit and X bar upper limit, such that what's in between is 95% of all the X bars. Okay, and we found out the values that the upper limit is you take your mu, which is right here, and you add to it. So you're going to get to this point right there. You're going to add 1.96 sigma over root square of n. And similarly, if you take mu and you go down, so you're going to go down by taking negative 1.96 sigma over roots of n, you will reach your lower limit. Okay, so I can rewrite all of this like that. So let me rewrite it. So I can say that as long as you have an SDM that is normally distributed, I'm trying to write an n here, then if you take mu And if you add and if you subtract 1.96 standard error or sigma over root square of n, well, that is going to capture 95% of the X bar. صح? صح. So let me draw it again just for the fun. So here's our STM. It has a normal distribution, and right in the middle you have mu. And if we said if you go up 1.96, you find the upper limit. If you go down 1.96, you'll find your lower limit. What's in between is going to be 95% of the X bars, and what's left out here you have 2.5% of the X bars, and here you have also 2.5% of the X bars left out. Alright, I'm going to name these different areas. I'm just going to give the names just to make my life easier. I'm going to call this area A. I'm going to call this area B. So B is just the 95%, and I'm going to call this area C. Okay. Now, before we continue, let me ask you a very simple question. If you pick X bar at random, okay, so the probability that X bar is gonna fall in area A, so the probability it's gonna fall in area B, and so the probability it's gonna fall in area C. Well, I think it's pretty obvious, right? I mean, if A represents 2.5 of all the X bars, then the probability that X bar is gonna fall in A, well, this is gonna be 2.5%. And if B represents 95% of all the X bars, then the probability if you pick X bar at random, then this X bar is actually part of B, then it's 95%. And if you pick also X bar at random, the chances that it falls in C is actually 2.5%. Okay? Just because the area A is 2.5%, area B is 95%, and area C is 2.5%. Okay. Now that we have established that, let me ask you the following question. How about I pick an X bar at random? Okay. So I'm going to pick an X bar at random, and what I'm going to do is I'm actually going to do, see this distance that I traveled up and down from you? Well, I'm gonna do the same thing, but this time for X bar. So now I'm gonna take an X bar at random, and I'm gonna go up and down that same distance. So I take an X bar and I add to it and I subtract from it 1.96 sigma over root square of n. And the question becomes, if I do that, will mu be inside this fence that I created, or will it not be inside that fence? This is the idea. Okay. Well, let's try and see. Let's say you picked an X bar that happens to be here. Okay. So this is your X bar right there. Okay. Now, if you take that X bar and you build that fence, the exact same fence that we did right here, so you're going to go up 1.96 and you're going to go down 1.96. Alright, so now you created this interval. Now, this interval right there, will it include y, or mu, I mean, or will it not include mu? Well, if you notice, mu is right here. So actually, mu is going to be captured by this interval, and the answer is going to be yes, mu is captured by this interval. And you shouldn't be surprised, right? Because when I picked this X bar at random, I picked it to be part of the B area, meaning I picked it up within a range of the 1.96 sigma over root square of n. Therefore, if you take that point and using that point you build the same range, well, of course you're going to capture mu. Let's do another example. Let's say you pick an X bar, and this time this X bar happens to be, let's say, here. Okay? So this is my X bar. And now I'm going to build around it the same fence, the 1.96 sigma over root square n. So this distance right here, if I take and I go up this distance and I go down that distance, now I have built this interval. My question, does it or does it not include mu? Well, see how it crossed mu? So yes, it will include mu, and mu will be inside it. In fact, as long as your X bar that you picked is inside this catchment area here, if you build that interval around it, you will capture mu. What if my X bar is not inside it? What if my X bar happens to be here, for example? Okay, so let's say this is my X bar. And again, I'm going to try this upper limit and lower limit. So I go upper and upper limit, I mean 1.96, and I go down. Okay, and now I build a fence. My question is mu, which is right here, right? Remember, this is mu. Is it inside? No, it's not. It's not inside, and you shouldn't be surprised that it's not inside of it, because it's not supposed to be inside it, because you started with an X bar that was far away, further away than this limit here, and therefore you shouldn't be surprised that when you build this fence around your X bar, then it will not include mu. Okay? Alright, so keep this in mind because I'm going to use it in a second, and let's recapitulate. So what did we say? Well, we said if you have a sampling distribution of the mean that is normal, if you take mu and if you go up 1.96 sigma over root square of n, sorry, yeah. So you're going up 1.96 sigma over root square of n, and if you go down 1.96, sorry if I'm not doing it very well, if I'm not drawing very well. Okay, so this area inside, we can consider now this area, we called it B, and it's going to be our catchment area, meaning that if you take an X bar and you build around it the same fence, 1.96 sigma over root square of n, the question becomes, is it going to capture mu or not? So is mu going to be inside? Yes. Or is it not going to be? No. Well, the answer to that question is very simple. It turns out if you started with an X that's inside area B, your answer is going to be yes. But if you started with an X bar that is either in A or in C, so either A or C, then the answer is going to be no. As simple as this. Okay? Alright, so here's the thing. If I have a population, I took a sample, size n, and I calculated X bar, and let's say you do not know the value of mu. Okay, you have no idea what mu is, but you took that X bar and you build around it the fence that we talked about a minute ago. So you took X bar and you added and you subtracted from it the 1.96 sigma over root square of n. If you did that, then will your, and so we call this now an interval, okay? هل interval will capture mu or will it not capture mu? I'm sorry about this. So will it capture mu or not? Well, it turns out that it's going to capture mu if you started with an X bar that is in area B, and it will not capture mu if you started with an area that is either A or C. Now the thing is, you don't know where X bar is, do you? You don't know. You have no idea where your X bar. But if you remember a few minutes ago, we said that the probability that your X bar is going to be in B is 95%, and the probability that it's in either A or C is actually 5%. So even though you do not know where your X bar is, you are 95%, you have a 95% chance that you are inside of B, meaning that you captured mu. Therefore, we call this a 95% confidence interval. And what this is doing is that it's taking your point estimate, which is X bar. So you're taking a point estimate, you're turning it into an interval estimate. So بعدنا بالestimation, but this is the last piece of estimation. And the great thing about this interval estimate is that now you can actually talk about capturing the real value mu, with the caveat that you're not 100% sure. It comes with a confidence attached to it. Okay, so if I want to summarize all of this I've been talking about, if I want to summarize it, this is what I would say. I would say that if you have a point estimate that is X bar, you can do an amelioration on that X bar by adding and subtracting a certain value, and by turning it into an interval. The plus and the minus is going to be, first you're going to take a Z value, and then you're going to multiply by the standard error, yani sigma over root square of n. That is called a confidence interval. Now, if you want to have a 95% confidence interval, then you would change the Z into 1.96. And then you would have a 95% confidence interval. Now, how would you interpret it? You would say that you are 95% confident that mu, or the real population average, because that's what you're trying to do at the end. You're trying to estimate the mu. And as we said at the beginning of the course, that most of the time we do not know mu. Okay, but at least you can say that you're 95% confident that this mu that we don't know is actually inside the interval that you created. Okay, and basically that's the interpretation of your confidence interval. So this is the formula of the confidence interval, and this is how you interpret it. And then you can use this to actually do some answering or inferential kind of answers that you can do. Okay, now I'm going to stop here, because the following video I'm going to do a recap, or I'm just going to use what you learned here to take it further away into the application. All right.